Question 1 from the 2025 Higher Physics Examination, Paper 1, the multiple choice. A car accelerates uniformly from rest and travels a distance of 18 metres in 3 seconds. The speed of the car at 3 seconds is, and you're given those following 5 responses. Well, this looks like a kinematic problem, and we put down our kinematic variables: u, the initial velocity; v, the final velocity; a, the acceleration; and s, the displacement; and t is the time. And we try to fill in as much as possible. We're told that the initial velocity u is equal to 0, so we put that in there. The final velocity is what we're after in this particular question, and the acceleration we don't know nothing about, so that gets left blank. And the displacement s we do know is going to be 18 metres, and we know the time that this takes place is in 3 seconds. So that's all we have. We've got initial velocity, we've got to find the final velocity, we don't know the acceleration, we can work out the displacement, and we have got the time. Well, the first thing I would think of is using the equation s equals ut plus a half at squared, because if I find the acceleration, then I can find the final velocity by putting it into the v equals u plus at. The initial velocity is going to be 0, so this equation is going to become s equals a half at squared. So we've got a simple equation to find the acceleration. Therefore, the acceleration is going to equal to 2 times the displacement, if we rearrange, divided by t squared. So we can find the acceleration, no bother. It's like a two-stepper problem. 2 times displacement is 2 times 18, divided by, and t squared is going to be 9. 3 3s are 9, and if we work that out, we're going to get an acceleration of 4 metres per second every second. Now, once we've got the acceleration, we can go back to the other equation, v equals u plus at, and we know that u is going to be equal to 0, so 0 plus the acceleration, which is 4, times the time is accelerating for, which was the 3 seconds, and we're going to have a final velocity of 12 metres per second, which is going to give us the answer of C. Now, there's another way we can do this question, and that's to do with the average velocity. We can say the following: we can say that the displacement s is equal to the average velocity times the time. So we can find the average velocity quite simply. The average velocity is going to be equal to the displacement divided by the time. So it's going to be equal to 18 metres, that's the displacement, divided by the time, and the time is 3 seconds. So we've got to have an average velocity of 6 metres per second. But what is the average velocity formula again? Well, the average velocity we can say is equal to the initial velocity plus the final velocity divided by 2. And therefore we can say that the average velocity is equal to just simply v divided by 2, since the initial velocity must be equal to 0. And therefore we can say that the final velocity v is just really twice the average velocity, which is going to be equal to 2 times 6 metres per second, and we get the same answer. We get an answer of 12 metres per second. No matter which way we do it, we get an answer of 12 metres per second. Question 2. A ball is thrown vertically upwards and then falls back to the starting position. Which of the following acceleration time graphs represent the motion of the ball? Now, what we have to recognise is when you throw that ball into the air, the minute the ball leaves your hand, there's no more forces acting on the ball except for the force of gravity pulling it down. So therefore there's going to be one acceleration acting on that ball, and that's going to be the acceleration due to gravity, which equals minus 9.8. So we're going to have an acceleration equal to minus 9.8 metres per second every second. It's the only acceleration acting on that particular ball. So if we look at the first graph, we can see that this graph here is going to be correct because the acceleration is negative and it's a constant acceleration. So we know right away that our answer to our graph is going to be that first one there, so we'll give that a tick. It's definitely that one. Let's look at the other responses. You can see part B, the acceleration is positive. Down, we've got 2 accelerations here. That's not the case. Only one acceleration acts in the ball, therefore that one is wrong. The C, we're going to have a varying acceleration, and that's not going to be right either. In fact, that's the graph of the velocity against time graph, just to confuse you. If we exchange the A with the velocity time graph, that graph would be correct. But since it's given us acceleration time graph, and it's given us a range of accelerations right down to 0 here, it's wrong. Part D graph, once again, that's wrong because acceleration is only one type of acceleration. It's acceleration due to gravity and it's constant. And this shows you acceleration which is not constant. There's various values of that, so it's not that one either. And our final one then is this one here. We can see we've got two accelerations again, a plus acceleration and a minus acceleration. That's wrong. When you throw a ball into the air, it's only got one acceleration, and that's acceleration due to gravity, and that's going to be represented by this first graph here. Question 3. A force of 10 newtons pulls a trolley of mass 2 kilograms along a horizontal surface. You can see the diagram there. The total frictional force acting on the trolley is 6 newtons, and we've got to find the acceleration of the trolley. Well, the acceleration of the trolley, A, is going to equal to the unbalanced force divided by the mass. And all we have to do is find the unbalanced force. Well, we know we've got 10 newtons in this direction and 6 newtons in that direction, so the unbalanced force, we represent by the resultant force, is going to be 4 newtons to the right. So we've now got the unbalanced force. 10 take away 6 is 4 newtons. So the acceleration is going to equal the unbalanced force, 4 newtons, divided by the mass of the trolley, which is 2 kilograms. And therefore the acceleration is going to be 2 meters per second every second. And that's going to give us the answer A for that one. 2 meters per second every second. Question 4 is a slope question. A block of wood of mass 3.5 kilograms slides down a slope. The block of wood has a constant acceleration of 2.3 meters per second down the slope. And we're told that the force of friction acting on the block is 6.4 newtons. And a little twist in this story is we've got to find the angle of the slope. Well, we know the forces acting down the way on this is going to be mg sine theta. So we'll mark that in the diagram. Mg sine theta is always the force acting down the way. That's the component of weight acting parallel to the slope, mg sine theta. And we've also got a force of friction acting back the way, and that's the value of 6.4 newtons. And we can find the unbalanced force, F unbalanced, because unbalanced force equals mass times acceleration. So the unbalanced force is equal to the mass times acceleration. We know the mass of the block, it's going to be 3.5 kilograms. And we multiply it by the acceleration. We're told the acceleration is a constant one of 2.3 meters per second every second. So right away we can work that out. We get a value of the unbalanced force to be 8.05 newtons, and that's going to be acting down the slope. So now we've got the value of the unbalanced force. All we need to do is find this force here, mg sine theta. So the weight component, as we call it, parallel to the slope, is equal to mg sine theta. And we know that mg is usually the weight. That's going to be 3.5 times 9.8. I'm going to get sine theta there. So we can find the value of that. It's going to be 3.5 times 9.8 times sine theta. We'll just leave it at the moment then. So if we look at our force diagram here, we can see that the force acting down the way, mg sine theta, take away the frictional force acting up the way, 6.4 newtons, should give us the unbalanced force. So we have the following. We have the forces acting down the way, which is going to be mg sine theta. We'll just work it out the side there in terms of 35 and 9.8. Take away 6.4 newtons must be equal to the unbalanced force, which worked out to be 8.05 newtons. Now we want to find sine theta here. We know what mg is. Mg is going to be 35 times 9.8. So we'll get a bracket 35 times 9.8 times sine theta. And that's going to be equal to, and it's going to be 8.05. Take the 6.4 over the other side, and we get that value there. And therefore we have that sine theta rearranged is going to give you 8.05 plus the 6.4. You can put that in your bracket, 6.4, put a decimal point there, divided by, and we've got a value of 35.98 to work out as well. 35 times 9.8. Now we go and work that out, then we get a value of sine theta. It's going to be the following value in your calculators. Sine theta is going to equal to a value of 0.421. So we take the inverse of that, theta equals sine -1 of 0.421, we get a value of theta, and the value of theta is going to come out to be, in this case, 24.9 degrees. And therefore we can put that into two significant figures, 25 degrees. So the answer to that will be letter D, and that's answer D, 25 degrees. A little twist in the forces problem, but very simple to do. All we have to do is establish the unbalanced force, get that done with. An unbalanced force is that there. Then we work out the component of weight acting down the slope, that's this part here. We can put that in there, and we know that the unbalanced force is going to be the weight down the way, the component of weight acting down the way, take away the frictional force acting up the way, and we get this expression here. Just rearrange to find what sine theta is, do it in your calculator, and sine theta is 25. Answer D. Question 5. An object is released from rest at a height of 1.6 metres above the ground. The mass of the object is 0.20 kilograms. And the maximum speed of the object just before it hits the ground is one of these responses. This is a conservation of energy problem. Here we have the object here at the top and the object falling down here at the bottom. Now at that height of 1.6 metres, it's going to have what we call gravitational potential energies. Up here we have gravitational potential energy is going to equal to mgh. Now, assuming all that gravitational potential energy is transferred into kinetic energy, just before it strikes the ground, the kinetic energy is going to be equal to 1/2 mv squared. Now, these two are going to be equal, so therefore we can say that the potential energy, mgh, has got to equal to the kinetic energy at the bottom, 1/2 mv squared. Now, do you notice we've got mass on each side, so we don't really need to use the mass, we can cancel the mass out. And we've got gh equal to 1/2 v squared. If we multiply both sides by 2, we get 2gh is going to equal to v squared. Take the square root of both sides, square root of 2gh, that's going to give us the speed v. So all we have to do is plug in the numbers and find out what v is. V is going to equal to the square root of 2 times 9.8, that's acceleration due to gravity, times the height which the object was dropped from, which is 1.6 metres. And we take the square root of that, and we end up with the value of the speed v to be equal to 5.6 metres per second, to two significant figures. So the response for that is 5.6 metres per second, and it's going to be B. It's a conservation of energy problem. You could do it with kinematics, you get the same answer. 5.6 metres per second is the maximum speed of the object just before it hits the ground. Notice how they say maximum speed, that's the theoretical maximum speed it's going to have if we ignore air friction and whatnot.